This is a flip video about strong acids and bases. So a few things to remember for this video is that we're going to be focusing on Bronsted-Lowry's definitions of an acid and a base. And if you remember from our previous video, in a Bronsted-Lowry acid, the acid donates a proton, an H+, and the base accepts the proton. Also something to remember is our generic reaction seen here. HA refers to just a generic acid, a hydrogen attached to some sort of an anion here. This could be HCl, okay? This could be H2SO4 if we wanted it to be. So this is our acid, and then water then acts as our base. Remember, water can act as an acid or a base, and we'll learn that in another video. In this instance, it's going to act as a base. Why? Because the H is going to donate a proton. How do I know that? Well, I look on the back end here to see what happens. Remember, start here and then look to see what happens. If I notice, H2O becomes H3O+. So therefore, I have accepted, right? Take a look here. The HA donates that H+, and H2O turns into H3O+. When I gain a positive proton, I get an extra positive on what was once neutral. And then what's left over? Well, my A is all by itself. The HA splits, so the A is by itself. Remember, the acid is linked up to a conjugate base, and the base is linked up to a conjugate acid. Okay, so those are some refreshers. Now we're going to focus on strong acids or a strong base. So everything I say about a strong acid, for the most part, can be applied for a strong base. So strong acids and strong bases dissociate completely, meaning every single acid molecule that's in your beaker of water will come apart completely, every single one of them, as well as if you had a base in there. Base plus water, every single base will dissociate. So all of my hydrochloric acid, all of my HCl molecules will dissociate. The H will come off of the Cl. And if you remember, the H again will come off, donate itself to the H2O, right? An acid donates to make H3O+, and the Cl- is going to be floating around in the beaker. We say it dissociates completely. They detach completely. Every single HCl. We use a single arrow, seen here, going in the forward direction, right? And that indicates that the forward reaction predominates. That's the one that's going to happen. It's going to go in the forward direction, okay? Now, what about a weak acid, or again, we can say the same thing for a weak base. Well, in a weak acid or a weak base, not every acid molecule will dissociate completely in that beaker. So if you notice here, I have HC2H3O2 thrown into water, right, dissolved into water. And I get over here H3O+ and C2H3O2-. So if you remember, my H is donated to H2O. That's why I get H3O+. And you notice here, here's the anion. C2H3O2- lost its H+. Now, not every acid molecule in the beaker is going to dissociate. And if you notice here, here's how I know that this is not a strong acid. Because my arrows give it away. I have both a forward and a reverse arrow. Okay? This double arrow indicates that the reaction can not only proceed forward, but it also can revert back. Okay, so my products can go back and turn into my reactants. Now, since the reverse arrow is drawn longer, it basically will show that the reverse reaction predominates, right? The longer arrow predominates, meaning this is what's going to happen more often, that my H is going to give itself back to my acid and form back into these. Okay? The double arrow means I have a weak acid or a weak base. The single arrow means I have something strong. So there is the key. I would write that down. So a few things just to kind of summarize here. Strong acid, remember, the water is the one that rips that H+ off. That H+ comes off because water, right, is a polar molecule with charged ends. And so it has a greater attraction for the H plus than the Cl did. So let's take a look here, right? HCl are attracted to each other. But as soon as you throw it into water, water, right, is polar. Water will say, I want it more than the Cl does. So that oxygen will snatch that hydrogen, right? It has a greater attraction for it. That's what's happening in a strong acid. In a weak acid, the water doesn't have as much of an attraction, right? Instead, in a weak acid, that ion right here, C2H3O2, this one has a greater attraction for the H. So it comes together more often, and the water does not have as great of an attraction. Okay? All right, the next concept we're going to learn is this. The stronger your acid, the weaker your conjugate base, meaning a lower attraction for the proton. And the weaker your acid that you start off with, the stronger the conjugate base will be, the stronger the attraction for the protons. Okay? All right, to look at this kind of in a picture, if you notice here, I've got blue little spheres that represent the H plus ion, a little bit of a bigger purple sphere that represent the A minus, so the anion. And put together, they're the generic acid, HA. A strong acid will have every single HA dissociated. We say it completely ionizes, meaning it completely turns into its ions, H pluses and A minuses. A weak acid, if you notice, will have a small amount dissociated. Notice dissociated, dissociated comes apart, but more are going to stay intact, stay together. That's what a weak acid beaker would look like. So very little ionization turning into ions, very little. Okay? I made this summary chart here of a strong acid and a weak acid. In the summary chart, in a strong acid, we learned the forward reaction predominates. In a weak acid, the reverse does. It's better to turn back into what you were. In a strong acid, the A minus is much weaker base than the water. So let's take a look at what that means in a strong acid. Oh, wrong one. Here we go. In a strong acid, the A minus, right, which is going to be the Cl here, okay, maybe I can bring back even the first slide. Let's go back to this. That'll help you. Sorry, here we go. We'll go with a generic reaction. The A minus, right, if this is a strong acid, which it is, single arrow, this A minus is going to be weaker. It's a weaker base than the water, right? The reason why is because the water says, I'm going to rip apart this acid and I'm going to steal that H and I'm going to keep it, right? For this reaction, the forward reaction dominates. As the A minus says, I don't have enough strength to pluck or to keep that H plus with me. I don't have enough strength. So this base ends up being stronger than this base, right? This one has a specific name. It's called a conjugate base, but we refer to it basically acting like a base. So this A minus is a much weaker base than the water seen here. Okay? Now for weak acid, the A minus is much stronger, okay, so than the base of water. So in other words, in this instance, because this is favored, this water is not going to be as strong as this conjugate. This conjugate base says, I'm going to steal back that hydrogen and turn back into this, right? This is what ends up forming, okay? All right. Here are a list of some strong acids that you should memorize and know. H2SO4, known as sulfuric acid, HCl, known as hydrochloric acid, HNO3, known as nitric acid, and HClO4, known as perchloric acid. Please have these memorized, both formula and name. If it is not a strong acid seen on this list, then it's weak. So there are more weak acids. So again, if it's not strong seen here, then it's weak. All of these, when you write these reactions, will have a single arrow. Lastly, we're going to talk about something called a monoprotic and a diprotic acid. Some definitions. A monoprotic, so just like the prefix mono means one, is an acid that can give or donate one proton, HCl. A diprotic acid is one that can give off two protons, H2SO4. So if you notice, it comes with two hydrogens, di for two, it comes with 1 hydrogen, mono for 1. Okay? Let's take a look at this last slide here. H2SO4 is a diprotic acid. And don't forget, it's a strong acid. So notice my single arrow. I throw H2SO4 in water. I can write water over the arrow, or I could have written plus H2O over here. Either way works. What happens? The 1H comes off first, and it turns into H plus HSO4 minus. Then the reaction happens again. Now my HSO4 goes through and thrown in water, and the next H comes off. So what's really important to note is that, first of all the water is going to go and rip off 1 hydrogen from every single H2SO4. So it's going to go to an H2SO4 and rip off 1. Then it's going to go to the next H2SO4 in the beaker, rip off 1. It rips off 1 from every H2SO4. Once it's done ripping off 1, then it will go back and rip off the second one. It does not steal 2. It steals 1 first from every single H2SO4, then it goes back and it'll go through and take the other one. Okay, that's the end of the video.